Yeah, thanks a lot. Yeah, thanks a lot for the invitation. Yeah, there will be some geometry. I'm not sure, maybe not some representations theory. I'm not sure about physics, right? Or wait, what is what are the GPRT? Yeah, sorry.
You covered all the bases. Yeah.
Okay, right. So yeah, I'll be speaking about Poisson-Lie groups, integrable systems, and the Berenstein-Kazhdan potential. You know, Poisson-Lie groups and integrable systems, these are two huge fields. So this will be just some very small portions and very partial view of those two things, even though I'll probably spend most of my time on giving some kind of adapted introduction to those two topics. In fact, Poisson-Lie groups, I think they originally they came up in the theory of integrable systems. So maybe more exactly, quantum groups were born in quantum integrable systems, and then people realized that one can go to some kind of semi-classical version. And then classical Poisson-Lie groups are very much related to classical integrable systems, but we're going to have a very, very special angle today. And the Berenstein-Kazhdan potential is a tool from representations theory that we'll see towards the end of the talk. So what I'm going to speak about is based on several papers, and they're joined in different combinations with Arkady Berenstein, Irina Davydenko, Benjamin Hoffman, Jeremy Lane, and Yanpeng Li. Okay, so as I said, I'll probably start just with introduction. Most of it is probably too elementary for the seminar, but yeah, maybe just for completeness, we still fix notations. So let me start with Poisson brackets and Poisson structures. So we say that M pi is a Poisson manifold if pi is a bivector, so a section of the second exterior power of the tangent bundle. And so having such a bivector, we can define a bracket between functions, between smooth functions on the manifold. So what we do, we pair pi, which is at every point is an element of the second exterior power, with the exterior product of differentials of our functions. So at each point it gives a number, so it gives a function on the manifold, and we would like this to be a Lie bracket. So that's the condition. Now, the standard examples of Poisson manifolds are so-called Darboux-Chads. So if we take an open subset in R2M, and we take the bivector, we denote coordinates P and Q with I running from 1 to M. So we just take those wedge products of d over dpi and d over dqi. Or if we go back, do you see my pointer or not at all? Okay, so if we go back to the brackets, then the standard canonical Poisson brackets of Pi and Qj are equal to delta Ij. A version of this construction are Toric Chads. So now we take an open subset of Rm, and we multiply it by the torus of dimension m. So here the torus is simply a direct product of m copies of a circle. And we take a similar Poisson bracket. So now we call coordinates on Rm lambda I, and we call angles theta I. So the coordinates on Rm, they're called actions. So here we get something which is called the Hamiltonian action of the torus. So this means that those lambda i's, if we substitute into pi now only one differential of a function instead of two, what we get is not a function, instead it's a vector field. And this vector field is exactly the fundamental vector field for the action of the circle with number I. So in total, all the lambdas generate in that way action of the torus. So in fact, for today, this is our poor man's definition of an integrable system. So an integrable system is a dense toric chart on a symplectic manifold. And in fact, we can relax a little bit conditions of being symplectic in the following sense. Here, in the definition of toric charts, I can add lambda i's which do not enter which do not enter pi at all. So then their Poisson brackets with everything will be zero. This will be Casimir functions. And that we also count as an integrable system. So in principle, we may have some number of lambda i's which is bigger than the number of theta i's. All right. So now a slightly more complicated Poisson bracket. Let me recall some standard fact. So suppose we have a vector space, and for some reason, let's call it V star. It's more convenient that way. So if everything is finite dimensional, so dualities don't pose a problem. So then linear Poisson brackets on that space V star are in one-to-one correspondence to Lie brackets on V. Just to say it in the same, this here, the next line is just saying the same thing. If you have a Lie algebra now, well, since it's a Lie algebra, it's denoted by the letter by this letter G. So then its dual space is Poisson, and here is the famous formula for the Poisson bracket. Basically, you have one lattice I, which is an element of G star, and two letters X and Y, which are elements of G. And more or less, you do everything you can with those letters. So the first thing, X and Y, define two linear functions on G star simply by duality. And we declare that their Poisson bracket is simply equal to a function on G star, which is associated to Lie bracket of X and Y. So the Poisson bracket on linear functions is by definition that Lie bracket. So this pi KKS, it's KKS stands for Kirillov, Constant, and Suryov, who one can say rediscovered that Poisson bracket, but on to Lie in his study, which introduced Lie groups. So that already, maybe somewhat implicitly, that bracket was known. Okay. Now, maybe one very, very standard example. So we take G equal to SUN. In this case, maybe I would delete, let me try to delete this S. I cannot do it now on the screen, but let's say G is equal to UN to simplify things. So then the Lie algebra, I can identify it with skew Hermitian complex matrices, n by n. And here, well, traditionally what one does, of course, G star, one can identify with G or do other things, but traditionally one identifies G star with the space of Hermitian matrices. Of course, in order to do that, we need to say what's the pairing. And the pairing is this slightly strange imaginary part of the trace of the product. So if you put the imaginary part of the trace, then skew Hermitian condition on the dual space will be replaced by the Hermitian condition. Now, here is the Gelfand-Zeitlin map, and it's going to inspire us in the rest of the talk. So this Gelfand-Zeitlin map does the following. You take your Hermitian n by n matrix, so it's here, this matrix psi, and you associate to it a triangular tableau. So again, I was supposed to draw some beautiful or maybe not so beautiful triangle around this Gelfand-Zeitlin pattern. So on the top row, we write eigenvalues of that Hermitian matrix. These are real numbers, so we can order them. And I order them, the first one is the biggest, lambda 2 is the next, and so on, till lambda n. So then we cut a corner n-1 by n-1, say, for instance, top left corner or down right corner, depends on your choices. And you take the eigenvalues. Now there will be n-1 of them. That's the next row, and so on till the corner 1 by 1. If we go to top left, this corner will be just psi 1, 1, and here is denoted lambda 1, 1. So lambda 1, 1 is simply equal to psi 1, 1. In fact, it turns out that all these numbers, they satisfy famous interlacing inequalities. You may learn them or you may teach them in the linear algebra course, but I think people rarely do. I think I learned those inequalities in some more advanced courses on functional analysis or theory of self-adjoint operators. But in any event, the inequalities are very easy. So now I'm sitting at this place lambda n1. It turns out to be bigger than everything else, right? In particular, bigger than lambda n-1, 1. But then lambda n-1, 1 is bigger than lambda n2, and so on. So we have a zigzag between the two rows, and this goes for every row. So of course, the inequalities are in general not strict. It turns out, so for our matrix, let's fix the eigenvalues. So let's fix the top row. Then it turns out that if you look through the matrices with given eigenvalues, you will encounter all the lambdas down there which satisfy.
We lost you for about 30 seconds there. So if
okay. Yeah, sorry. So I was speaking about, I was describing those interlacing inequalities. So if I start with lambda n1, it's bigger than lambda n-1, 1. Of course, because lambda n1 is bigger than everything. But then maybe somewhat surprisingly, at least I recall when I first saw it, I was surprised, lambda n-1, 1 is bigger or equal than lambda n2. And so on. So there is a zigzag between the rows, and between each pair of neighboring rows, there would be this zigzag of inequalities. In fact, if you fix the eigenvalues, so if you fix the top row and you ask a question, what are the possible other rows that you may get from matrices with those eigenvalues, you will get everything which satisfies the interlacing inequalities. All right, perhaps I would like to cite here, so I'll be citing some number of classical results and also some number of some more recent results. So there is a theorem of Gilman and Sternberg, which says the following, I'm not sure they would agree with this formulation, but it kind of summarizes several results. So in addition to those lambda variables that we call, because they're called lambdas, they will naturally be action variables. One can introduce angle variables. So this would be functions on some dense subset of Hermitian matrices. And each of these variables takes values in a circle. And in fact, those angles, there will be smaller number of angles than actions. So the top index now only goes to n-1. So you see, if we go back to the tableau, to the triangular tableau, or something that was supposed to be triangular tableau, then we don't touch the top row. So we associate angles to all the rows with the exception of the top row. And then it turns out that in these variables, this pi KKS, remember there was a linear Poisson bracket, it takes this form as on the Toric chart. So, and this is called the Gelfand-Zeitlin integrable system on the dual of SUN. It is, it looks simple, but it is still somewhat surprising, right? We have some linear bracket, and now we find coordinates, or we find variables in such a way that it becomes constant. And maybe it's interesting that on top of it, we are getting those inequalities, this triangular tableau for the action variables. So in fact, people were trying to do the same for other types of compact groups. And there were many partial results, because I don't want to mention those partial results, but it's a great recent result by Hoffman and Lane, who were able to do exactly the same thing for all compact groups independently of the type. So, I think, how is it, if I'm not mistaken, the Gilman-Sternberg result, that's probably the end of 80s, something like that, or maybe even the beginning of 80s. And so the result of Hoffman and Lane is of the end of last year. So it took some time. So today, the aspect of it that we will be interested in, we would like one of the questions we want to answer, at least in some ways, to better understand how those action angle variables come about, and also maybe to have some insight into the origin of the cone. So we denote this cone defined by interlacing inequalities by C. And we would like to better understand where it comes from. And eventually we also discuss the cones that Hoffman and Lane obtained. So, so that was,
Anton,
yeah.
Can I ask a small question? Could you remind us what this dense subset is defined by?
Oh, okay. So,
I mean, unless it's too long an explanation, and then I don't want
to hide it from you. But if you're asking, I think if all the inequalities are strict, right? So that's a pre-image. So we have this cone defined by the interlacing inequalities.
Yes.
And we consider the interior of that cone where all the inequalities are strict, and we take a pre-image.
Okay.
In fact, maybe one more remark about it, those lambdas are actually smooth functions. And when some of the inequalities become non-strict, they lose smoothness. They start behaving like some square roots or something.
Mm-hmm.
Right. Okay. So one of the tools, or maybe the second topic in the talk, is Poisson-Lie groups. In fact, I don't quite know. Basically, almost every time I have to speak about Poisson-Lie groups, it's difficult to produce a good talk out of it. I don't know what's your background about those polygroups, but usually people get confused. But okay, let's give it a try. So a Poisson-Lie group is a Lie group together with a Poisson bracket, for which the product, the multiplication map, is a Poisson map. So Poisson structure is a bivector, so it maps along the arrows. So in particular, G cross G to G, you can map the sum of 2 copies of pi on 2 copies of G here to 1 copy, and they should be the same. So this is a highly non-trivial condition, and it implies 2 things, among others. First of all, at the group unit, or I think at the group unit, the Poisson bracket necessarily vanishes, and it will be important for us. And then, one would think that maybe we are doing Poisson structures in the category of groups, but it's not quite true. For instance, the inverse, you cannot make it Poisson. If the product is Poisson, then the inverse has to be anti-Poisson. So the Poisson bracket changes sign. However, today we will be mainly concerned with compact Polygroups. And then there is a beautiful theorem, which I also twisted a little bit. It's due to Lewandowski-Sullivan in the 90s. And it says that such a pi, which is non-zero, assume it's non-zero, is essentially unique. So essentially, I'm cheating here a little bit. It's not completely true. So even with this up to disclaimer, but let's assume it as if it were unique. So it's of course unique up to possible rescaling. I can always multiply by some real numbers. And also I can apply conjugations on the group. These are automorphisms of the product. So I can always map by conjugation one Poisson structure to another, and I still get a Poisson structure. So there is some canonical choice with those two disclaimers, and it's called the standard Poisson structure. Well, here I wanted to give you an example of a Poisson structure on SU2. Maybe, you know, maybe we can skip it for a moment, and maybe in the end I will just, because I wanted to give you examples and exercises, to be honest. Now, well, I wanted to write explicitly, or maybe I still do it. Let me try. So let me write it on the board. So okay. So the Poisson bracket on SU2, just for you to know how roughly it looks like. Typically, these are quadratic Poisson brackets. So we were discussing up to now constant and linear Poisson brackets. So those are quadratic. Let me recall that this is a real manifold. That's why I have to write also Poisson brackets for the complex conjugates. So this is not a holomorphic world. And then a bar is whatever minus 2i b bar. Well, well, since I already wrote it, check that a bar square plus b bar square is a Casimir function, because right, we want to put it equal to 1, so it better has vanishing Poisson dispersing. Okay, may I take away the board and return to the file? Okay. So okay, good. So now there is this interesting notion. I don't quite know to what extent you're familiar with it, which is called Poisson-Lie duality. So given a Poisson-Lie group, you always get a companion, a second Poisson-Lie group, which comes, and it works as follows. So let's start with a Poisson-Lie group G pi. Then we said that pi vanishes at the group assume that everything is very nice. Let's say we take the Taylor expansion of pi at the group unit, and we take a linear term of it. It turns out that it defines, of course, it's linear, right? Because it's a linear term of Taylor expansion. It turns out that it's again a Poisson structure on the tangent space at the group unit, and the tangent space at the group unit is the Lie algebra. Then by the yoga that we reviewed a little bit, one-to-one correspondence between linear Poisson structures and Lie brackets, this means that there is a Lie bracket on the dual space. We denote it by the bracket star. Now there is the following theorem due to Greenfeld and Semyonov-Tinshansky. Again, I somewhat took a liberty to assign it to them. I think they did prove it, but I don't know whether they would agree on the wording. So there is a unique connected and simply connected Poisson-Lie group, let's call it G star pi star, such that the Lie algebra of it is this G star bracket star, and the linearization of this Poisson bracket at the group unit of E star, right? By symmetry, it should define a Lie structure on G, which is which would be the dual of the tangent space at the group unit of G star, right? And we want this Lie bracket, the corresponding Lie bracket, to be the Lie bracket that we started with. And one can go one way or the other between G star and G. Of course, maybe G was not simply connected, then we'll recover its universal cover, but basically it's a correspondence up to the fundamental group. And there is always a companion Poisson group. Now, here is a theorem of Liu and Weinstein, which tells us how those Poisson-Lie groups, dual Poisson-Lie groups, look like if we choose G to be compact with the standard Poisson structure. In fact, complexification of our compact group, there is the KN decomposition where the compact would be G itself. And then it turns out that G star is isomorphic to this AN. So it's a subgroup, it's a simply looking subgroup of the Borel. Maybe just to make it a little bit more clear,
Okay, it looks like we've lost Anton. Okay. He is still there in some.
Yeah, sorry, people. Today seems to be really capricious, right? Okay.
No problem.
Okay, so I think, right, we parted when speaking about Borel. Is it right?
I think so, yeah.
Okay. So in the case, yeah. So in the case of SUN, here is how it looks like, this G star. These are simply upper triangular matrices. The strictly upper triangular entries are complex valued, and the diagonal entries are positive reals, and their product is 1. Note that also this G star
Oh. Okay. Let's hope that when he comes back, it works out.
multiplication. All right. Here there is some explicit formula which tells you what pi star is. That maybe.
Okay, this is unfortunate. Yeah, okay. Anton, are you back with us?
Yes.
Okay,
yes.
Maybe.
But I don't quite know what.
Yeah, so I'm not sure what's going on. Do you want to, shall we try my sharing your file, see if that helps?
Yeah, okay, let's try your sharing.
Okay.
So,
Okay, how's that?
yeah, very good.
All right. So then we will go to, shall we go back to here?
Yeah, right. Where did you where did I decouple?
Basically around here, as I recall.
Okay. So so here this theorem explains to us how the example how G star looks in the example where G is SUN. Then you see it's kind of, maybe if you've never seen it, it's slightly surprising. This G star, it's not at all compact. Instead, it's solvable. This is a subgroup of upper triangular matrices where you have positive reals on the diagonal. And see, if you want SUN, then the product of those reals will be 1. Note also that by the Iwasawa decomposition, G star is also isomorphic to the quotient of the complexified group by the compact one. And because of that, it carries a left G action. So you can still multiply on the left. And then there is a loop formula which explicitly tells you what this pi star, what this bracket pi star is, but I suggest we skip it. So this is just, I just wanted, if we had more time, it would be fun to explain it, but it's a short formula. But let's go to the next slide. And the next slide tells us how it looks like for the star of SU2. So these are tri-2 matrices. B is complex valued, A is real and positive, and here are the Poisson brackets. So they are all quadratic in matrix entries. At first sight, right, there is nothing special about them. So let's go to the next slide. Okay. And here is, by the way, I don't quite know, is green well visible?
Yeah. Yeah.
On your screens? Okay. So there is a famous result by Ginsburg and Weinstein. And again, we start with G compact Poisson-Lie group with a standard Poisson structure. And then there is a Poisson isomorphism between the linear Poisson structure on small G star and this mysterious, or whatever, this more complicated quadratic Poisson structure on capital G star. So in principle, we would be interested to know how this isomorphism looks like. And basically, the explicit formula is only known in one example, that's G equal to SU2. And in this example, that's the somewhat cumbersome but explicit formula that you see on the rest of the page. Perhaps let's go to the next slide and I'll tell you more about Ginsburg-Weinstein. So, so this theorem, it has, right, up to now, it has several proofs in literature. Well, not as many as the Pythagoras theorem, but still quite some number, which are done with different techniques. So the original argument proof was some kind of chronological argument. That's how Ginsburg and Weinstein proved it. And then together with Eckhard Manneken and myself, I designed some number of proofs which are using the Moser lemma from symplectic geometry. And then there is a proof by Bolch using the Stokes phenomenon. And Xiaomen Xu, he was able to make some kind of concrete formulas out of it, because typically these matrices, they're not very concrete, with the exception of SL2, he was able to consider some particular cases. Then there is some kind of PDE based on classical dynamical R matrices developed by Enrique Setzenhoff and Marshall. And we also designed another proof using quantum groups, using so-called Dirichlet twists. So the second question we want to discuss today is to better understand this gamma. So gamma is a kind of mysterious and complicated object. And maybe if we, for a second, go back to the previous slide. Thanks. So one problem with gamma is, you can compose it with an arbitrary Poisson automorphism on the left and on the right. So it's not unique. If you want to make it unique and you get some more explicit description, you need to make some choices or impose some conditions. Maybe that's one of the problems why it's difficult to study it. So, so basically, these are our two questions: how to better understand those action angle variables, those lambdas and thetas, and also how to understand this gamma. In the rest of the talk, I'll try to convince you that maybe these two questions are related. Right now, they are not very related to each other. They're in somewhat different fields, but now we'll try to put them together. Okay, so let's shift by 2 slides forward. So there will be some number of observations that we're going to use. The first one is a very easy one. So let's call it scaling. As I said, the Poisson-Lie on small g star, this pi kks, is linear. So if we simplify the relation, so multiply x by some real number, let's say positive one, then what's going to happen? The kks bracket will scale. It will also multiply by x. Now, if we compose this gamma, suppose we've chosen some gamma, then we get a map to G star with a bracket pi star, which is also scaled by s. Now the idea is as follows: gamma is a complicated map. Even for S2, it's not very pleasant. So the hope is that if we send s to infinity, then maybe it simplifies. And we'll see that in some way this is the case. So many things simplify, maybe even the composition gamma s simplifies. No, gamma s is still Poisson map for all s, right? So we can multiply our pi star by 1,000 or million. So it's right. So let's go to the next slide. And let's introduce one more. Right. So you see, if we simply multiply by s and send s to infinity, the end is going to explode. So it's no good. So we need to do something with coordinates. We need to cleverly choose coordinates. Here, the theory of class algebras so you see, yeah, it tells me every time that it's going to be recorded.
Yeah.
So we have those
Anton,
funny
sorry to interrupt you. Eva was suggesting that maybe you should turn off your video. Maybe we can do all the same. I don't know if that may facilitate.
Okay, sure. Yeah, absolutely.
I mean,
yeah.
It can't hurt.
Yeah, let's give it a try. Yeah, absolutely. So so we have those funny coordinates. They are inspired by the cluster structures on Borel. And you see the log of the absolute value is scaled with s. So that's the funny feature. In fact, this in what follows, we'll see gamma s is a kind of hugely expanding map. And this map to alphas and phis is a hugely contracting map. So this in this way we get some set of coordinates, and this is an example of SU3, but we can do it for all the types. And so we call them alpha, beta, and phi. Phi are angles, and alpha and beta are real numbers. So this gives us some coordinate system. And if you go to the next slide, maybe we can do the following. Let me denote this coordinate system by delta S, right? It depends on S. And let me denote by pi S the Poisson structure in those coordinates. This means that if we map this R to some power times the torus to G star using those coordinates, then this pi S will be mapped to S pi star. And here is one of the results that I wanted to present to you today. It's due to Berenstein, Hoffman, Lie, and myself. And also it's a kind of combination of many things, but I'm formulating in the following way. So there is a unique polyhedral cone inside this R to the power M plus R with the following two properties. First of all, on this cone, this pi S has a limit when you send S to infinity. And this limit is some kind of toric chart type, right? This Poisson structure is constant, and these are vector fields d over d lambda I, where lambdas are some linear combinations of alpha and beta, and the angles are the angles phi. These were just the phases of complex numbers. So it's already like somewhat surprising, right? It didn't look at all that there would be some limit. And also it's strange, this limit is only on that cone. Outside the cone, nothing good happens. It probably explodes. In fact, we don't know, but I think in most places it simply explodes. And then there is another interesting feature, the symplectic leaves of this constant Poisson structure. In fact, those symplectic leaves, what are they? So they are some kind of intersections of hyperplanes with a cone, so some kind of polytopes times the torus. So those symplectic leaves are in one-to-one correspondence with generic symplectic leaves of the KKS bracket. So with generic coadjoint orbits. And under this one-to-one correspondence, the volumes coincide. So the symplectic volumes of the leaves of this pi infinity and of the coadjoint orbits, they are the same. So this is a kind of strange and interesting and surprising observation. In some way, it already a little bit ties the different ends, right? So G star is involved with this map gamma, and we now have those toric charts which come up by themselves. And maybe we can look at the next slide, and there I can tell you a couple of more things about it. First of all, what is this cone C? At least since the Berenstein-Kazhdan potential was in the title, I should tell you what it is. So it's a function on the Borel, a complex valued function in general. And I wanted to give you an example in the case of SU3, but I wanted it to be interactive, and I wanted to say what function it is. Unfortunately, now you only see like the preparation for explaining what the potential is. Now let me tell you. So basically, this will be a sum of ratios of minus. And in the first fraction, the minor in the denominator, this should be simply the upper right corner. So just the matrix element in the upper right corner. And in the numerator, this will be the shifts of this matrix element. The first one, say, would be to the left. So this would be whatever, U12. And the second one would be down there from upper right corner, one step down. This would be U23. Well, sorry for like spelling it this way. So this is U12 plus U23 divided by U13. And now for in the next fraction, it will be the ratio, but now of 2 by 2 minus. So the minor downstairs, it's the top right 2 by 2 corner. So this is 1, 2 by 2, 3. And the 2 minus upstairs, you shift either one column to the left, or you shift one row down. So basically, it's always the same scheme. So this Berenstein-Kazhdan potential, they invented it for arbitrary type. So it is some rational function, roughly of the type that I described for you now. Now, what is the cone C? You put the angles equal to 0, and then phi becomes a sum of exponential functions, where in the exponents you have linear functions of alpha and beta. So this is actually an interesting exercise. In the SU3 case, you can do it. And surprisingly, the denominators, they are monomials, right? For my statement to be true, the denominators have to be monomials. There should be no sums in the denominators, and it turns out to be the case. So for instance, this element U13, it turns out to be a monomial in terms of those exponentials. You can check it by multiplying those 4 matrices on the previous slide. But but it turns out to be the fact for in all cases. And C is singled out by the condition that all those linear functions are negative. So that's so it's a polyhedral cone because you have a finite number of linear functions, so that's how it works. Now. You see, it's also kind of interesting and surprising for the Poisson bracket to have a limit. In the Poisson bracket, you would also have some exponential functions. And to have a limit in those exponential functions, when s goes to infinity, all the L's need to be negative, right? Because if they're positive, the Poisson bracket would explode. So, but Poisson bracket is many functions. So a priori, you would have some huge number of conditions. Now, phi is one function. In phi, there are many conditions, but still they are kind of quite condensed. And it turns out that if those conditions in phi, they are verified, if those L's are negative, then all the L's that you would encounter in Poisson brackets, they would also be negative. So that's an interesting and surprising fact in combinatorics of cluster varieties. In fact, we still don't quite know why it really works that way. So a Poisson bracket is a kind of interesting tensor. Phi is a function. Of course, it would have been much more reassuring if there were some kind of algebraic relation between phi and the Poisson bracket. One can imagine from other geometries, like a Keller potential, right? A Keller potential defines for you a symplectic structure on a Keller manifold. But now phi is related in some way to the Poisson structure on G star, but we just don't know how it is related exactly. Like the features are related, but there is no algebraic formula. Maybe one more slide to see some kind of picture, just to, I wanted to here to draw a little bit how it all happens. Well, I'm not sure my drawing is very clear, right? So this thing on the left is the polyhedral cone C. It's multiplied by a torus. So this green triangle, right? It's supposed to be a kind of triangle inside the cone. That's a leaf of pi infinity. So the bluish thing around it, that's a leaf of pi s, for s very big. You see this leaf of pi s, it approaches the green triangle, but it also goes outside the cone, somewhere very far. And this leaf ls is the leaf of pi kks. It's isomorphic to it. But you see what happens when S becomes very large, all the symplectic volumes, it concentrates near the green triangle. And eventually the part of the bluish thing, which falls on the green triangle, it collects all the symplectic volume. By the way, the proof of the fact that the symplectic volumes are the same, our proof is probably not optimal, because what we have to use a lot representations theorem. So we associate so-called tropicalization to the Borel, and this is some integral cone. So this is a set of integral points in the cone C, and a priori they parameterize bases in representations of the length-length dual G check. But then one can also negotiate that there is a relation to representations of G. And after this negotiation, one can establish the relation to the symplectic volumes of coadjoint orbits. So this is a rather roundabout way. Perhaps there is a simpler way to do it. Maybe we go to the last slide, because, well, my time is up already almost 10 minutes ago. And let me state a conjecture.
Anton,
yes.
can I ask you a question? Sorry, I missed something. I'm sorry. This gamma S that you're scaling, right? This linearizing map. Which one is it? Because you described several approaches to it, but you said, obviously there isn't a unique one. So did you mention which one it was that you're scaling, or you're scaling any one of them?
No, but up to now we haven't used it. So that's now that we are entering the game. Your question is right. It's just some seconds ahead of time.
Okay. Well.
Yeah, but we are now discussing it.
I'm usually half an hour late, but anyway.
Yeah. So suppose we choose some gamma. So then we can compose it with this delta S minus 1. So we'll get in that way a map from linear Poisson structure on small g star to constant Poisson structure on this product of the vector space and the torus. Now we hope that there exists a gamma such that the limit when S goes to infinity exists. So I'll tell you a little bit more about it. If it exists, it will more or less automatically be densely defined in Poisson, and its image is very likely, almost surely, be the product of the cone times the torus. You see, it would kind of explain basically all the things at once. It will give you some kind of nice formula for the limit of gamma. Well, gamma itself is kind of complicated, transcendental, but its limit is a nice thing. It will also tie together the linear Poisson bracket on G star and the constant Poisson bracket on those alpha, betas, and phi's, on those tropical coordinates. So basically, this would be answering all the questions. And in the case of SUN, Lane, Lee, and I, we were able to prove it. But that's essentially because in that case, there is a very good choice for gamma that Meinrad and I invented some time ago. And there we were able to impose many conditions on gamma, which chose just one map. And that map has a nice limit. Now, whether one can do it in the general case, we don't quite know. But as I mentioned, there is one explicit computation by Xiaomen Xu, who computed gamma in some limiting case of the Stokes phenomenon procedure. And for that one, it does not converge. The action variables converge, but the angle variables, they start rotating very, very fast when you send S to infinity. Probably one can fix it by some canonical transformation, but at least at the moment there is no obvious way how to choose that gamma. We know that sometimes it exists. Probably it always exists, but we don't yet know how to choose it. So if you show the next slide. So then I can say thank you, and well, and I apologize for all those breaks. I don't quite know, that's that's not how it was intended. But thanks again for the invitation, and well, for also thanks a lot for kind of staying with me till the end.